This is Paul, the SDR guy, and this is part 4 of our ongoing SatDump series, and this is episode 27. In today's video, we're going to get a very good introduction to SatDump's image product expressions. If you'd like to learn how to create this RGB composite and a whole lot more using image product expressions, then this video is for you. To begin this video, we're going to need to learn some possibly new definitions and learn a bit about the calibration units. We will be using some different temperature scales. So here you see Kelvin, Celsius, and Fahrenheit, and you should just quickly review and refresh yourself here. So the three calibration units we're going to speak about today are albedo, brightness, temperature, and radiance. Well, what in the world is albedo? Well, it's how much an object reflects light. It comes from a Latin word meaning whiteness, and it's commonly measured from 0 to 1 or 0 to 100%. 0 means all the light is absorbed. In other words, none is reflected. So, perfect black. 100 means all the light is reflected. So, perfect white. Brightness temperature. The temperature at which a black body, in other words, a body that has an albedo of 0, would have to be to emit that specific quantity of energy that is measured by the satellite. If the wavelength is approximately 10.5 micrometers, then this so happens to actually match real surface temperature. That's within limits. Hence the name thermal IR. Since it's a temperature, it's measured usually in Kelvin, but can also be expressed in Celsius or Fahrenheit. Radiance, the radiant flux, and that is the power in watts that's emitted for emissive radiance or reflected for reflective radiance by a body per unit solid angle, per unit area. Its unit is naturally the result of this definition, watts per steradium by meter squared. Take a moment to learn more about a satellite's sensor. Broadly speaking, you can define 3 groups of channels in a satellite sensor. Emissive channels. These are wavelengths that emit radiation and are not affected by the sun. Number 2, partially reflective channels. These are wavelengths that emit radiation but are also affected by the sun, and they reflect back some of the light from it. And the third one is reflective channels. These wavelengths are not emitted at all unless the surface is illuminated by the sun. Here's an emissive example, thermal IR. and this is a wavelength longer than about 4 micrometers. That includes also water vapor lines that are in the neighborhood of 6.7 and 8.7 micrometers. These are purely emissive channels. They aren't affected by the sun directly. The only effect is that if the sun is shining on the water, then it will heat up, hence emit more. But it takes time due to thermal inertia. These channels don't reflect anything off the sun, so they can't be calibrated as albedo, obviously. They are calibrated as brightness temperature or emissive radiance. We're now going to look at a partially reflective example. Shortwave IR channels, wavelength between about 3 and 4 micrometers, are partially reflective. 3.75 micrometers used at night to detect fog is a prime example. Earth emits some radiation on 3.75 micrometers at night. However, during the day, some of it is also reflected off. The behavior of that specific channel changes drastically between day and night because of the reflection from the sun. This is also in addition to the heating effects mentioned in the previous slide. Since those have both a reflective as well as an emissive component, they can be calibrated as both albedo for reflective radiance or emissive radiance / brightness temperature. Let's now look at a reflective example. Visible and very short IR, wavelengths shorter than approximately 2 micrometers, appears completely black at night because the Earth doesn't emit any radiation in those wavelengths at night. If it would, we'd all be dead. Think about a red hot piece of metal in a steel mill. We see something only because the sun's light is reflecting off the Earth. Since these channels don't emit anything at the temperatures experienced by the Earth, and we want to emphasize, fortunately, then they cannot be calibrated as brightness temperature or emissive radiance, but only as reflective radiance or albedo. Let's continue. We're now ready to continue with image product expressions. What is the function of image product expressions? Well, if we look at the SatDump documentation, it says the image product expression system is specifically used to generate more or less complex RGB composites from an image product. Well, what do image product expressions do? Well, they act like a formula for building an image, telling SatDump which channels / bands to use, how to combine or transform them, how to map values to colors, and how the final image should look. We are going to learn by doing, so we're going to create several different examples using image product expressions. And the first thing that we're going to do is we're going to launch SatDump. Once it's up and running, go to load first party and load the GOES 19 full disk images. Make sure you download daylight images. We will use the GOES 19 product to learn how to create image product expressions. And so the question is, what if we could find recipes for RGB composite images using ABI bands? Let's begin with example number 1. And what we're going to do is we're going to be creating a true color RGB composite using the GOES ABI bands. A quick Google search will provide us with this page. This is a quick guide, and it gives us the recipe, and these quick guides generally always show you how to decode the colors that you will see in a final image. That will become more apparent in our future examples. So this is what the actual recipe looks like. So it's telling us red. Then here we've got a formula. And the ABI sensor does not have a real green band, if you will, but it does have a band that is sensitive to chlorophyll. And so by doing this formula here, 0.45 times red plus 0.1 times what is referred to as the veggie band plus 0.45 times blue, this will give us our green. Lastly, we have the blue, and what we need to do now is we need to find which bands these particular wavelengths are. And so here we can see 0.47 is blue, 0.64 is red, and 0.86, and this is band 3, so just bands 1, 2, and 3, is veggie. As always, the links to all these different resources will be put in the video notes. I will also be putting the image expressions for each of the examples in the video description as well. So we're going to continue, and we're going to make an actual screen video of us working through example. So a bit earlier in the presentation, you were directed to launch SatDump, then go to the file drop down, load first party, and we did show you that in one of the prior videos, and you were to select an image that a full disk image of GOES 19, and you want to make sure that you chose one that's daylight, so that way we can see most of the earth. And so I've already done that. And then I've also taken the time to make just some text notes to myself here. So we're going to need in our formula here, we're going to need to use red. And so red is channel 2, and we need to specify this so that red is first, then green, and then blue. So we're going to start here with red, and then the green is, and actually let's make some space here, and let's say green is equal to, what we're doing is we're building a macro here, and we're going to say 0.45 0.45 times red, and we know red is channel 2, and we're going to add that to 0.1 times the veggie band, and that's channel 3, plus 0.45 times blue, and blue is, we scroll down here a little bit, is channel 1. And when we're building these macros, we need to end the line with a semicolon. And so we can make a red macro, and again, semicolons are required, and a blue. So at this point, I can delete my notes that I was using to implement all of this. And so when it comes time to actually display the RGB composite, order is important, and it needs to always be red to begin with. So we're going to type red, and this time we're going to put a comma here, and then we're going to do a green next, and then a comma again, and blue. And at this point, we can go ahead and ask SatDump to apply this image expression. So I'm going to click on apply here. This does take a bit of time. And once it finishes applying, it will take a little bit of time for it to actually be displayed for us. And there we go. The scale has been changed, so I'm using my mouse wheel. And how about that? Another thing I like to do, pardon me, is come down here to Image and click on Remove Background. Now at this point, you might be tempted to think you're done. And if you did, you would be incorrect. What we really need to do is we need to calibrate each of these bands and use it in our image product expression. So what bands are we using? We're using 1. So let's go here, and actually we're having to wait a minute for the remove background to complete. These are large images and a lot is taking place here, so you have to be patient to allow it to complete. Okay, it has now been removed, and so we're using 3 different channels, so we need to calibrate 3 different channels. Let's begin with channel 1. So we click the drop down, we select channel 1, and you can see calibrate, and we're going to click to the left of that. And what we want to do next is we want to add this to the calibration. So we're going to say add, I'm sorry, I misspoke. We want to click add to the expression. And so you see that right there. And so we need to do the same things for channel 2. and we're going to add that to our equation or expression. You have to be patient between these steps because, again, it does take some time to do this. And there's channel 2, and let's do channel 3 next. There we go. Let's add this to our equation. So notice there that at the beginning of each of these channels, they've added another C in front of the channel number. That means calibrated. Calibrated channel 3, calibrated channel 2, calibrated channel 1. So what we're going to do is we're going to come down here to our formulas and we're going to add the calibrated channels. So that's calibrated channel 2, here's calibrated channel 3, and here is calibrated channel 1. And we're going to come here and we're going to use calibrated channels in these two places as well. And we are ready to go. So let's go ahead and apply this. And again, this is going to take a bit of time. Once again, you have to be patient while this process is working. All right, here you go. This is your very first super cool looking image product expression. We will continue with example 2, and this one is called day cloud type. Once again, we do a Google search and we find the quick guide, and the quick guide basically tells us what all this particular uh, image is going to tell us. And it also gives us a RGB recipe. And here it is. And I want you to notice here that we've got a new thing called gamma that we're going to need to include. So here's band 4, the wavelength 1.38 micrometers, gamma 0.66, so on and so forth. And you can see what these colors relate to. So what we're going to do now is we're going to do a screen capture of us building this image product expression. Okay, we still have the image here from example 1. I've just deleted the expression for this, and I've made myself some notes here that so I don't have to keep referring back to the day cloud type RGB recipe. So we know that we have channel 2, we have channel 4 and a 5. So channel 2, we've got channel 5 or channel 4. Let's put them in order here for the time being. And we learned that it's important for us to calibrate things. So let's go ahead and do that. Let's bring this up. Channel 2, calibrate is on, and let's wait for that to work its magic. And once again, we're going to have to wait. We're going to now move to channel 4. And lastly, we're going to calibrate channel 5. Okay, we have all of our channels. So let's make a macro for red. So red equals, red is channel 4, and we're going to use calibrated channel 4. Now, we have to add gamma to this. Well, how do we do that? Well, we're going to use the caret character, and if you hit shift and the number 6, you'll see the little caret pop up there, and we're going to put 0.66. And remember, this is a macro, so we need to put a semicolon at the end of it. So let's do green. And we know that green is, we're using channel 2. And we see that has a gamma of 1. And then we have blue. Blue is going to be calibrated channel 5 and also a gamma of 1. Again, you've got all of your macros have the semicolons at the end. And so I'm going to remove my notes now. And we're ready for red, comma, green, comma, blue. And we're going to go ahead and click on apply. And here we have our final product. And once again, if you want to understand what all of these colors mean, that's where you go to your quick guide to find out. So this concludes example number 2. We're going to now move to example 3. This is where we will create a Severe Storms RGB composite image using ABI bands. And here's a quick guide. Once again, it shows you a recipe, how to read the image when you actually create it. As I've said throughout the video, all links will be included in the video description. So here we go. Here is the recipe. And you may notice something that looks a little strange here with the temperatures that are in Kelvin. Notice here, Kelvin, it's showing a range of -35 to +5. Well, the lowest you can go with Kelvin is 0. So this is strange right away. Same thing for when we look at the next row, the green, and this is a clue that we need to use what is known as a split window. And so, you're going to be asking yourself, well, what in the world is a split window? Well, a split window in satellite imagery is a technique that uses two closely spaced thermal infrared channels to improve measurements. Now, this is a simplified example or definition or explanation of a split window. It will suffice for now, but there's much more to know about split windows. So in this case, we're going to need to use a special calculator. And it just so turns out that let me go ahead and minimize the presentation. And look, here is the website URL, and what we do is we plug in the numbers, and you can compare these numbers with the recipe. And we're going to use the brightness, temperature, and Kelvin. We're going to use 200 and 400. Here is where we type in the numbers minus 35 and 5 for red. Then we come down here and we click Create Equation. And this equation that you see at the bottom is what we're going to be using in our image product expression. So this one is for red. And if we come over and do the same thing for green, click Create Equation, and it pops out at the bottom. And then lastly, the blue, and you see it here. And let's return to our presentation and move to the next slide. So what we're going to do now is we're going to actually build this expression within SatDump. In the interest of saving time, I'm just going to copy my image expression in here. And I'm not going to go through and explain this line by line because I've already done this in previous videos. So let's go ahead and apply this expression. And as you can see, the storms really pop here. So this concludes example number 3. We're going to now look at the last example, and in this example, we're going to use a LET. And in this particular case, we are going to look at NDVI, and that stands for Normalized Difference Vegetation Index. And there is a formula that you can see here, tells you a little bit about the infrared reflectance, the red reflectance, and then here is color as depicted in the LET here. So let's continue. And here's the actual LET that we're using. And this LET has been slightly modified to also cope with sea surface, as the sea absorbs most of the radiation in the visible and shortwave infrared. And that is, it has a very low albedo. It can be detected fairly easily. And this LET is a 1D LET. SatDump already has an image product expression for NDVI, and I'm going to explain how it works. So here we're calibrating our channels, and we're specifying the path to the LET, and then we have the red, green, and blue macros. And this one's a little bit different. And notice there's something in the middle, equals 0, and then a question mark, and then a value, then there's a colon, and then there's another value. Same thing for both the green and blue. Well, how does this work? Well, this is an example of the ternary operator, the question mark true, colon false. And this ternary operator is akin to an if-else statement in any other programming language. So this statement before the question mark is evaluated. And if it is true, then it uses or does whatever's the first thing after the question mark and before the colon. If this first expression is false, then it does the second thing. And I also want to remind you whenever we use a let name, we're identifying the X position, the Y position, and then lastly the let channel. This, and I'm going to copy my image expression in here. And there we go. And I'm going to now apply this. And here we go. And this is a very interesting RGB composite. The darker green areas is where the most vegetation is. For example, if you look over South America, you see very dark green in the area of the Amazon. This concludes example number 4. I want to thank Lego 11 for his major contributions to this video. I learned a great deal about SatDump image product expressions during the creation of this video. I hope this video helps you understand how image product expressions work and the tremendous value that they can provide to satellite imagery. I'd like to thank you for watching today's video. Please consider liking the video and subscribing to the channel. Have a great day.